Okay, so according to my notes from Mrs. Vaughter, this is where you guys left off yesterday with the mail carrier question. Right, so here, quick review. Work energy theorem. Work is a change in energy. Mechanical energy specifically, okay? But in the case of Science 10, we are going to have situations only where either potential energy is being changed by work or kinetic energy is being changed by work, okay? So any work energy theorem question starts out the same way and generally follows the same pattern. All right? Very much like predicting chemical reactions was in Unit 1. Once you learned the pattern, it was pretty easy to follow. Work energy theorem questions do the same thing. Okay? So, what we have to do with a work energy theorem question first is ask ourselves, after reading the question, what kind of energy, potential or kinetic, is being changed here? Right? So in this question, a mail carrier picks up a 10 kilogram package, that's probably an important number, okay, on the third floor of a building 30 meters above the ground. Okay, what do we call a measurement above the ground? Height. Okay, so that's probably my initial height. Okay, we can confirm by reading the rest of the question, but for right now we're going to say that the initial height's 30 meters. Okay, and then delivers it to the 10th floor. Okay, we were right, 30 meters was the initial height. The 10th floor, which is 100 meters, is our final height. Okay, how much work is done? Looking for work. Okay, so work is definitely happening. Okay, here's what I want you to do when you read one of these questions. Visualize. Okay? If you were to be given a 10 kilogram package, that's around 25 pounds, okay? And you were told, carry it from the 3rd floor to the 10th floor up the stairs. Would you have to work hard to do that? I mean, it's hard enough going upstairs. I'm old, so it's harder for me, okay? But that's the price you pay for athletic prowess in your youth, okay? So, you carry this box. It's heavy, okay? You're going to have to work hard to carry it up 7 floors on the stairs. It never says that they use the elevator. Okay? The elevator would then do the work. This person is carrying this box up the stairs. They're going to be tired when they get there because they've done what? Work. Okay? Envision yourself doing that. Would I get tired? Would this be hard work? If the answer is this would be hard work or yes, it's a work energy theorem question. Then you got to ask yourself, okay, in doing that work, what energy is changing? In this question, the person is taking it from the 3rd floor to the 10th floor. What kind of energy is changing? Potential. It doesn't talk at all about the speed of the package, which probably means the person just walked up the stairs at a uniform speed and never changed the kinetic energy of the box. Unless the box's speed changes, there's no change in kinetic energy. This only mentions the change in height. Okay, so this is basically like the first step. I've identified that in this question, potential energy is changing. In order to change potential energy, we have to do work. The question wants to know how much. Okay, now we already know. There's 2 ways to calculate work. Work can be force times distance, or it can be a change in energy. In this case, we're not given any of that. So this time we're going to use change in energy. Some questions you'll put force times distance equal to the change in energy. We'll get to those. All right. Do I have a formula that calculates potential energy? Anybody remember what it is? M times G times H. Okay? You don't have to memorize that. It is on your formula sheet. You probably want that out most of the time here going forward. All right. So work then is going to be potential energy final, because whenever we calculate change, it's always final minus initial, agreed? Okay, so it'll be my final potential minus my initial potential, and as we just said, the way to calculate potential energy is to go mass times gravity times height final minus mass times gravity times height initial. Right? Those formulas would calculate how much energy the 10 kilogram package has on the 10th floor and how much it has on the 3rd floor. Agreed? Okay. What do I do now? Do I have all those numbers?
Yes.
I know the mass. I have to assume this is on Earth. Okay? And I know that the initial height's 30 and the final height's 100. I've got all the numbers to plug in on the right side of that equation. Okay? So that's what I'm going to do next. I'm going to actually calculate the final answer to this question, which is the work the person carrying the box is going to have to do. 10 kilograms times 9.81 times 100 meters, so that's the first part, minus 10 times 9.81 times 30 meters. Okay, everybody all right with that? Okay. Okay, so when I punch that into my calculator, okay, you probably don't have to bracket it, but I generally do. Okay, so I'm going to have 9.81 times 10 times 100. Sorry, I did that in the wrong order. Doesn't matter though. Okay, minus 10 times 9.81 times, not minus, times 30. Okay, so there's my calculation. All right, 6,867 joules. Are you talking about the math trick where I just go m times g times 70? Yeah, good. You could totally do it that way. I never demonstrated it because it tends to confuse people. But you got a math mind, you figured it out, you can do it. Only for potential. Can't use it in at 1/2 mv squared because v is squared. Doesn't work there, but it works here. If you didn't understand a word of that, pretend you never heard any of it anyway, because this way will work too. Okay? All right, so 6,867 joules. Okay, does that sound like a lot? It is a lot. I could go have like the Big Mac meal now after that. Okay, with the big fries and the big drink, probably even a milkshake. That's a lot of calories. Okay, that's a lot of joules. I would have used a lot of energy to carry that box up the stairs. Okay, this is what, like, if you've got like the Fitbit or your Apple Watch or whatever, okay, they're constantly, if you let them, spying on you and recording your position, your altitude, all that kind of stuff, and that's how they calculate how many calories you burn in a day. Okay, they look at stuff like this. If you've gone up in altitude, okay, how far have you gone according to your GPS position? All that stuff is used to calculate calories you burn in a day. Okay? If you're interested in that kind of thing, okay, your watch is doing that, or your phone is doing that if it's in your pocket all the time. Okay, doing that all the time. Because what am I at now? Ooh, I got all my steps already. See, and all my heart points. Woo! Yeah. Okay. All right. Sorry. Okay, this one makes sense. All right, so all work energy theorem questions go like this, okay? I write down my givens. I figure out from the context of the question what kind of energy is changing, okay? If the height's changing, then it's potential. If the speed is changing, then it's kinetic, okay? In Science 10, you'll never have a question where both change. It's the absolute first thing we do in Physics 20, okay? But you don't have to do it. It's actually not, it's actually easier because you just know everything is changing and you just go with it. Okay, here you actually have to figure out which one's which. All right, then you have to plug in your formulas. Maybe you have to do a little bit of algebra. On this one we really didn't, okay, but on some we will. Okay, and then calculate your work. Okay. All right, so as I was saying here, we know that work is a change in energy. Okay? And we just calculated work by calculating the change in potential energy. That's one way to get it. The second way to get it is to multiply force times distance. They're both work. Okay, so think about this. If you are, let's say you got like a wheelbarrow, okay, and you pick it up and you're pushing it along, okay, and accelerating it, are you using a force? Okay, are you moving through a distance? Then you did work. How do you know? The wheelbarrow went faster. Okay, you changed the wheelbarrow's kinetic energy. This is the thought process you need to go through on every question. Okay, what's happening? What is required to make that happen? And is it changing energy? If so, what kind? Okay, because oftentimes, since this equals this, and this equals this, then this and this are also equal. Okay, and that's where the things will go. Then there'll just be some algebra, moving things around, adding, subtracting, multiplying, dividing, okay, stuff you've done before. All right, I want you to write that one down and give it a try. It's very much like the last one we did. Okay, but again, read the context of the question, figure out what kind of energy is changing, okay? Set up your work energy theorem, manipulate and solve. The manipulation's a little trickier on this. Okay, you got to do a little bit more algebra. I shouldn't say tricky. You just have to do more algebra than the last. Okay, first question we're supposed to ask ourselves is work being done in this question? Yep. Okay, we're moving a truck with a bulldozer. Okay, and we're taking that truck from 2 meters per second to an unknown velocity. That would seem to imply to me that the velocity is going to change here. Agreed? So what kind of energy is changing? Okay, kinetic. All right, so in this question, the work being done is going to change the truck's kinetic energy. The things we know the work. That's nice. Don't count on getting that all the time. Okay, 7,500 joules saves us a step. And it's pushing the truck from an initial velocity of 2.0 meters per second to an unknown velocity. And the mass is 2,500 kilograms. Sorry, I got messy. Kilograms. Everyone with me so far? Okay. So work, which is a number I know, is the kinetic energy final minus kinetic energy initial. All right? I'm going to leave you there in case you were stuck to that point. Okay? Now see if you can get kinetic energy final by itself and then put the formulas in to see if you can isolate what we're trying to find, which is VF. Okay, I'll give you a couple more minutes and then we'll walk through it together. Okay, so in this question we know that the kinetic energy is being changed. We know it's being changed by 7,500 joules because that's how much work was being done. Okay, now if it were me, before I go plugging in formulas, before I go plugging in numbers, VF is what I'm looking for. Would that be part of EK final? It would be. So let me get that by itself before I put in the 1/2 mv squared. It's way easier to move right now when it's just a letter than when it's 3 different numbers. Okay? So what I'm going to do is try and get EKF by itself by doing what with EK initial? Adding it. Okay, so here's why this should make sense. Work is a change in energy. If I add the change to the initial energy, should that give me the final? It should, right? Okay, so this logically also makes sense. So if I take the change, the work, and I add it to the initial kinetic energy, that should get me the final kinetic energy. Now I would put in my formulas. Okay, so this is 7,500 joules. Okay, this is 1/2 times the mass. 1/2 times the mass, sorry guys, times m times vi squared, and this over here is 1/2 times m times vf squared. I want to get vf by itself. What do I do with the 1/2 and the m? Divide them over to the other side. Okay, that gets me vf squared. I just want normal VF. What do I have to do? Square root it. This is about as tricky as the algebra gets, but in the end, I'm still following those same 3 rules. What I do to one side, I do to the other. Okay? Square root of both sides. The square root of VF squared is VF. So, okay? All right, so now what I want to do is put in all my numbers. So the work, 7,500 joules, plus 1/2 times 2,500 kilograms times 2 squared, that was my initial velocity or speed of the truck, and then divide that by 1/2 times 2,500. Now, at this point, sometimes people make a little mistake. People are like, oh, 1/2 of m is on the top and the bottom, I can cancel it, can I? No, there's an addition subtraction operation on top. Okay, if all these numbers were being multiplied, or divided, you could absolutely cancel it then. okay? But this is basically in brackets on the top, divide by the bottom, okay? So that won't work here, but I see sometimes people do it. All right, so if I plug all those numbers in, and guys, honestly, there's two ways to do this. The way that I usually do it, which means I forget numbers, so I'm really careful when I enter, or the one that means remember everything and get all your brackets right or you're screwed. Wait, okay? So what I usually do with something like this, okay, is I go, all right, I've got 7,500 plus 0.5 times 2,500 times 2 squared. All right, there's the top of the equation. I'm going to divide that by the bottom, 0.5 times 2,500. Now I've got that. Then I'm going to take the square root of that. Okay, final velocity of the truck is 3.16 meters per second. Did it speed up very much? Went from 2 meters per second to 3.16 meters per second. But it's a heavy truck. Okay? That means the bulldozer has to do a lot of work to push the heavy truck. Okay? So it's not an unreasonable number that its speed didn't change by very much, by 1.16 meters per second. Okay? If you've ever seen a truck stuck in mud, okay, it takes a lot of work from other heavy machinery to get it moving. Okay, so the way I did that on the calculator is typically the way I do things, one step at a time. If you're really conscientious and really good with your calculator, you could do it this way. Whoop. See, I'm not even conscientious enough on my calculator to do it this way. 2500 times 2 squared and bracket divided by in brackets 0.5 times 2500 bracket. Okay, yeah, I did it right. Okay. I mean, if you want to keep track of all those brackets, you can totally do it in one step, but I think it took me longer to do it that way than it did to do it the other way. Okay. And if I miss a bracket, is it going to be a mess? Show your work. Okay? When you get to this point, it's really easy to make a mistake on the calculator. Show your work. Okay? All right. So, just a set of steps here. Sometimes people like to have steps to follow. Okay? So I'd like you guys to write these down. These are the steps to solving a work energy theorem problem. Okay? We've already talked about them. We've done them on every single problem. Okay? I will say and walk through these steps every single time we do one because they always work. Okay? So once you use these steps a few times, you won't need to refer back to me. Just have them. Okay? But let's have you write them down for right now, okay? And then we'll do a couple more. Okay. Let's have you guys try this one. This one has one little weird thing in it that you get from the context of the question. It's probably going to throw you off a little bit, but that's why we're using it as an example. Okay? So in this one, write it down. A person uses an unknown force to lift a 50 kilogram mass, that's like 110 pounds or so, okay, to a height of 1.5 meters. Okay? How much force was used? Okay? All right, give you a few minutes, write that one down, give it a try. I'll talk you through the steps again, kind of one at a time, give you time in between. Okay guys, let's just walk through like the first couple of steps here. Okay? The givens and the type of energy, okay, the first two steps. All right, so first let's do the type of energy. This person is lifting something. Okay? What kind of energy is changing? Potential. Okay? It doesn't mention any, are there any speeds given here? If there's no speeds given, then the person is not changing the kinetic energy of the object. They're just lifting it. And they're lifting it from the ground to a height of 1.5 meters. How did I know they were lifting it from the ground? It says to a height of 1.5 meters. Where do we measure height from? The ground. This is what we call a contextual clue. Okay? It doesn't outright say it was from the ground. It doesn't outright say the initial height is 0. We have to get that from the context of the question. Okay? It doesn't ever say it was lifted from anywhere other than the ground. And then it says to a height of 1.5 meters. If they wanted it to be from this height to this height, they would give you both. Okay, so this is one of those, it's an assumption, but it's a safe assumption to make in this question. Levi, question?
Yeah, if there is no initial height, shouldn't we just say it?
Well, I mean, that's kind of what we're doing. We're saying I wasn't told outright the initial height, but I have to assume in this case it was 0. Okay? I mean, generally that's where people lift things from. If they're going to lift to a height of 1.5 meters, that's to about here. You don't do that from a height of 3 meters. That's lowering. Agreed? Okay. So I'm going to say then that the mass is one of my givens, 50 kilograms. Okay? I'm going to say that my initial height is what? 0. Okay? That makes my final height 1.5 meters. Now, this question wants to know how much force was used. Okay? Now, if I want to get force, I need one more thing, don't I? What else do I need? Distance. This is the thing that's like makes people uncomfortable about this question. They think they have to do it, but it seems wrong. Okay? If I lift something 1.5 meters, do I have to exert a force over 1.5 meters? In a question like this, it comes up. It's not all the time, but it comes up. In this question, the distance and the height are the same number. Okay? When you lift something from the ground to 1.5 meters, you exert a force over 1.5 meters. You can't let go of it in the middle or it's not going to keep going. Okay? Everyone kind of follow me there? It's just one of those weird things, okay, that sometimes happens. Okay? Now, if you're looking at that and going, I didn't even know I needed distance, here's why you needed distance. We already identified that in this question, potential energy was being changed. I was never told the work. Okay? They want the force. Remember, there's 2 ways to calculate work, right? I can calculate work by going force times distance, which I think I have to use if they want to know force, and by calculating the change in energy. Those are the 2 ways to calculate work. A few slides ago I said, hey, those 2 things can be equal. This is the first question where that happens. Okay? I would say here that if work is changing the potential energy, that means the force I exert over the distance is equal to the change in potential energy. All right. Hopefully that, if you were stuck, hopefully that helps you. I'll give you another couple of minutes to finish it off from there. Okay? Remember that we are looking for force here. Okay? Okay, give you like 2 minutes and then we'll run through the rest of that one. Do I get to cheat a little bit here? Can I make this formula a little bit easier if I recognize one thing? What's the one thing I have to recognize? Right, there's only final potential energy. If something's sitting on the ground, it can't fall any further. What's my initial potential energy? Right. Subtracting 0 doesn't do anything, so I can just get rid of that. Okay, that happens sometimes. If your initial energy is 0, you just get rid of it. Okay, whether it's kinetic or potential. If it's 0, get rid of it. Okay, don't need it on there. Okay, so now I'm looking for force. What do I have to do with D? Yeah, just divide it over to the other side. It's just algebra now. Okay, divide both sides by D. All right, so force is going to equal the final potential energy divided by D. All right, so that's going to mean M times G times H final, that's my formula for potential energy, divided by the distance. Now, here's the math trick. You don't have to do this, but if you recognize that you can, do it. This number and this number, are they the same? Then they cancel. If you want. You don't have to. You get the same answer either way. Okay, so I'm going to plug in my numbers here. Mass was 50 kilograms. G is 9.81 because we're assuming this is on Earth. That's another contextual clue. If they don't say Mars or something, you're on Earth. Okay, times the final height, which was 1.5 meters, and then I divide that by the distance, 1.5 meters. In this case, because everything is being multiplied on the top, there's no addition or subtraction. 1.5 divided by 1.5 is 1. Doesn't matter, you don't have to do that, okay? You can totally enter all of it. So 50 times 9.81 times 1.5 is that, whoop, not 1.5. Okay, and then divide that by 1.5. Okay, 490.5, what are the units per force? Newtons. Okay, incidentally, that is the weight of the box. Probably looking at me going, Coderre, the weight of the box is 50 kilograms. No, it's not. Okay, weight and mass are two different things. Mass is how much of you there is. 50 kilograms in this case. Okay? Weight is how much gravity pulls on your mass. Okay? You feel somebody's weight. If somebody sits on you, you feel their weight. Okay? Gravity pulls their mass down onto you, you feel their weight. Okay? Their weight would be different if they were bigger or smaller. Okay? Being sat on by a 3-year-old is different than being sat on by a sumo wrestler. Okay? They have different masses, thus they have different weights. Okay? So, here's something you can do. I mess with people all the time when they do this. Okay? Hey, how much do you weigh? That is an incredibly inappropriate question to ask anybody, by the way. Okay? You know, unless you're like two, hulking, muscular people who just work out all the time, then it's okay, maybe situationally. But at a party, you don't say to somebody, hey, how much do you weigh? Because I tell them, I weigh 785 newtons. I don't have to say what they wanted to know, which was how many pounds my mass is or how many kilograms my mass is. I tell them my weight. And then they chuckle awkwardly and you can go somewhere else because they don't want to talk to me anymore, which is perfect because I'm kind of an introvert. Okay? And that's a rude question. But I don't have to lie. I just tell them what my weight is. And they have no idea what my mass is, which is what they really want. Okay. It's a trick you can play on people. Take your mass in kilograms, multiply it by 9.81. That's your weight. It's in newtons. It's fun. It makes you feel smarter than other people. Okay. Let's do this one. We'll see how this one goes. Okay. Now, we talked about the ramp. Okay, a couple days back. We talked about how pushing something up a ramp and lifting it to the top were the same amount of what? Work. And the reason for that was you changed the potential energy of the object by the same amount. So spoiler alert, now you know what kind of energy is changing in this question. Okay, but this is a classic work energy theorem problem. I have put ones like this on exams before. Okay, I'm going to give you a few minutes to work on that one. Let's do the first two things for this one. So the box is being moved up this ramp, it's being pushed up the ramp. Okay, we know its mass is 35 kilograms, so we can start writing down some givens here. All right, we know that the mass is 35 kilograms. Okay, it's being pushed up a hill by a force of 150 newtons, so they gave me force. Okay, over a distance of 25 meters. All right, so they gave me distance. That would be then the length of the hill. Agreed? If it's being pushed over a 25, that's the length of the hill then, right? Essentially what we're looking at is this situation here, right? This is 25 meters long, and the box is here, and it's going to there, right? That's the visualization part. It's okay to draw pictures, okay? They don't have to be pretty, none of mine are, okay? But that's what's happening. That box is being pushed up a hill. Pushing is a force. Okay? The length of the hill is the distance. Am I doing work? Okay, here's the second part. What kind of energy am I changing about this box? It's potential energy. It is going from the bottom of the hill to the top of the hill, and they want to know how much higher is it than it was at the where? Where's the reference point here? The ground. Okay, I started at the bottom of the hill. I'm going for somewhere else, 25 meters lengthwise, okay, up the hill. What I'm looking for is how much higher up the hill am I? I'm not 25 meters higher, vertical is higher. Okay, I'll have gone 25 meters, but how much higher am I? That's another contextual clue. They didn't outright say that initial height was 0, but we can assume they're referring to the bottom of the hill here. Everybody okay with that? All right, so we've just identified then, and we identified it before, okay, that in this question, the work is changing the potential energy. Okay, so I'll leave you to go from there. Give you a couple more minutes before we do the rest of it. So let's look at the rest of this. We know that we've got a force pushing this up the ramp over a 25-meter distance. We know that that is going to change the potential energy of the box. Right? So we've set it up that work is changing the potential energy. Okay? I know the force, I know the distance, so I'm going to put those two things in for work, because that's one of the ways to calculate work. Okay? But if I'm going to get the final height, then I'm going to have to go m times g times h final minus m times g times h initial. Right? I'm still saying work is a change in potential energy, right? Can I get rid of anything? Exactly. Subtracting 0 doesn't change your mathematical operations, so we can get rid of that. I just want to find the final height. What do I have to move? M and G, yeah. Okay, so all I'm doing is dividing M, G, over to the other side. Okay, did that end up being a very mathematically complex problem? But there's a lot of thinking that goes into it. That's what's challenging about physics, getting to the math. The math is never all that hard, it's getting to it. Okay, so now I've got that set up. I can calculate my final height. So final height is going to be the force, 150 newtons, times the distance, 25 meters, divided by, what was the mass? 35 kilograms, times acceleration due to gravity, 9.81. Okay, so in brackets on the top. Okay, 150 times 25 divided by 35 times 9.81. All right, so 10.92 meters. That's how much higher we are now than we were at the bottom. Right? So essentially, what we're looking at is a ramp that looks like this. It's 25 meters long, and it's 10.92 meters high. If we were good at geometry, we could figure out the angle of the hill. We could figure out the incline using sine, because I have the opposite and the hypotenuse. Okay? If I wanted, I wouldn't do that with you guys. All right, everybody okay with how that works? All right, guys, we're going to do lots of these. But here's the thing I promise, so pack up, please. Okay? The algebra is always going to be like this. Okay, you're just going to be moving some things around. And you know what? First, it looks intimidating, but you're going to get used to it. Okay, the big thing here is to visualize the problems so that you can walk through those steps. Okay, visualize yourself pushing a heavy box up a ramp. How is that going to work? Are you going to get tired? What are you changing about the box? Okay, visualize all those things. It's the most important thing you can do to be successful in physics. Okay, the math will take care of itself. Okay, it's never going to be much harder than this. Okay, moving a couple things around. Okay, so as I said, we're going to be doing a lab soon, probably this week on work. Okay, we'll do a lab next week on energy, and then the following week you're going to have your unit exam. Right, so it's coming up. Okay, I'll put a review out probably next week. Okay, for you to start looking at.